Today we'll show you how to modify the TP456 charging board to increase its charging rate. I have these Tesla Model 3 21700 batteries that need to be charged. The problem is the TP456 board max out at 1 amp. The Tesla batteries, they are 5 amp hour, so if I charge these at 1 amp, it will take a very long time to charge these. So it would be nice to increase the charging rate of the TP456 board so that I can charge the Tesla batteries faster. And luckily on the TP456 board there is a programmable resistor, and it's right here, that allows you to increase or even decrease its charging rate. Let me use a magnifying glass so you can see clearly that resistor right there, 122. So the actual value of that resistor is 12 and then 20 after it, or 1200 ohm or 1.2 kilo ohm. Here's the formula to calculate the current that goes out to the battery I got from the TP456 spec sheet, and the V programmable is given at 1 volt. So the current that goes out to the battery follows this formula, and because the R programmable is 1200 ohm, which is this resistor right here, we got 1200 divided by 1200 and we got 1 amp of current, which what this TP456 board is maxed out at. So with this formula here, in order to increase the current output, we have to reduce the resistance, and I want my current output to be 2 amps, and therefore the R programmable should be around 600 ohms. This resistor is right now 1200 ohms. There are two ways I can make this 600 ohms. The first way is to remove this resistor and put in a 600 ohm resistor, and because this resistor is so small, it's pretty hard to desolder and remove this resistor and put in another one. Another way to make the total resistance 600 ohms is to put another resistor in parallel to this resistor, and you can make the total resistance 600 ohms that way. So here is the formula to calculate the total resistance using two resistors connected in parallel, and from here I can deduct the total resistance using R1 and R2. So here's how R1 and R2 is wired in parallel. I know the R1 is 1.2 kilo ohm. I don't know the value of R2 yet, but I know the total value should be 600 ohm between here and here. So by using this formula, I can calculate R2. I know R1 is 1.2 kilo ohm, R total 600 ohm, and I can calculate R2 using this formula, and it turns out to be 1200 ohms, which is in this case exactly the same value as R1. And here it is. So instead of soldering the external resistor directly onto the internal resistor on the board right there, it's kind of hard because the legs are hard. I use a couple of wires to solder it in first and extend it out, and that will make my job a lot easier to solder the 1.2 kilo ohm resistor onto the wires instead. I have my meter here, and let's just double check to make sure. 0.599 kilo ohm, so that's 600 ohm. That's right on. Right now we have less resistance and more current, and therefore more heat applied to the chip, so we're gonna need a heat sink to cool it down, otherwise it will burn out. I have a piece of aluminum about 2 millimeter thick. I cut it into smaller piece, and then I cut it into little slots, and then I use my vise and bend this up 90 degrees, and this is what I end up with, and that's a new heat sink for the TP456 chip, and it's going to be on here just like that. If you don't have this aluminum, and you can use heatsink from an old circuit board, from an old computer or TV. This aluminum can be easily cut with an aviation snip, just like that. Next step is to put the heatsink on the chip itself. I'm going to use my homemade thermal paste to put on the chip, And because this is made of mostly graphite, it's very electrically conductive. I'm going to use double-sided tape and just tape on and cover up the leg on both sides of the chip, and just like that. That way, if some of the thermal paste is spilled out of the chip, it doesn't short out the legs. And here is the thermal paste. I'm going to spread a very thin layer. And now I would just mount the heatsink on the chip just like that. And because there's nothing here to secure the heatsink to the chip, I'm just going to use zip tie. Here it is. I loop the zip tie around and it's on there good. It's very secure. Alright, I've got everything connected, ready to test. I got my Tesla Model 3 21700 cell connected to my battery holder / testing rig. I've just made this, and I'm going to show you that in my next video, I promised. Now let's turn it on. See the blue light on. It's on, but it's not charging because there's a switch here. Once I flip the switch, it will start charging. You ready? Boom. Red light on, and it's charging at 1.7 amps, 1.8 amps. That's pretty good. I've got my thermometer here. Let's see how hot it is right now. Okay, 29 Celsius maximum. Let's just put the timer on and start. Alright, we're about 16 minutes in, and the charging current is about 1.5, 1.6 amps. Now let's check on the temperature. Temperature is very stable. I would say around 43 to 45 Celsius. And it's just a little bit warm. I can touch it with my finger and I can hold it there. The heatsink is doing a very good job to cool down the chip. And the battery voltage is 3.94 volts. Alright, so we are almost 1.5 hours in. Battery is at 4.2. And the current goes down to 1.2 now, 1.1 now, so we're getting there. And temperature on the heatsink has been pretty stable, around 42 Celsius. And right now, because the current is lower, it's getting cooler. It's right now at about 31 Celsius max. Alright, it's been 3.5 hours and it's just been done. You can see the light on the unit is blue. And battery voltage is exactly 4.2 volts. So that works perfectly. Let's check out the temperature on the heatsink. It's a chilling 17 degrees Celsius. So according to my calculation, if the resistor R2 is 1.2 kilo ohm, R total should be 600 ohm. And if R total, aka R programmable, is 600 ohm, my current output should be 2 amps. So as you can see, my calculated output is 2 amps, but the actual output is only 1.6 amp. So I've got 0.4 amp unaccounted for. And that is because this is lost as heat. And that energy went into the heatsink. And I do want to achieve 2 amps output, or at least as close to 2 amps as possible. So I'm going to replace this 1.2 kilo ohm resistor with a 1 kilo ohm resistor. So if R2 is 1 kilo ohm, then R total or R program should be 545 ohm, and my output to the battery should be 2.2 amps. Some of this will be lost as heat, but at least I will get closer to the 2 amp output as possible. At least that's the theory. Let's put it to the test. Alright, I've replaced with a 1 kilo ohm resistor, and now let's double check with my meter. Our total should be 539 ohm, which is very close to the calculated value. Mathematics is amazing. Alright, I got a new discharge Tesla battery ready to be charged. And let's start. 1.7, 1.8 amp. We are 28 minutes in, almost half an hour, and the output current is still the same as before, 1.5, 1.6, and the temperature on the heatsink is about the same as before, 43 degrees Celsius. The current output should be more than this, but I'm getting exactly the same. Well, it's even less. So I think I'm reaching the limit of this board. So to confirm this, I'm going to put in a lower value resistor and see what happens. Check out my new resistor. How ridiculous does that look? I need an 800 ohm resistor, which I don't have, so I put 4 of these resistors in series, totaling 800 ohm. Then I put that in parallel with the original 1.2 kilo ohm resistor in here. And according to this calculation, our total should be 480 ohms. And let's double check that with my meter. 476 ohm. That's right on. And the calculated current output should be 2.5 amps. Let's find out if that's true. 1.5, 1.6 amps. That's it. So there you have it. I have reached the maximum limit of this TP456 board. The maximum current output is about 1.5, 1.6 amp. It doesn't matter how low the resistor gets. So to sum up, the best way to do this is to put a 1.2 kilo ohm resistor in parallel with the original 1.2 kilo ohm resistor on the board to get the maximum amount of current, while at the same time have a minimum amount of heat and wasted power. And that's all I have for now. Thanks for watching, and I will see you next time. I have a piece of aluminum. I think it's about 2 millimeter. 2 millimeter.